Hi everyone, this is Sayyid Abir Mukhtar Hussain, and I am recording this video as a requirement of the second assignment of our course of robot manipulation. So basically, in this assignment, we were asked to design a robot using the inverse kinematic functions that we have studied in such a way that the robot should be able to reach some destinations in its workplace. So the task was that we have to keeping in view this diagram, we have to design a robot whose center is placed at this point. The origin of the robot is placed at this point where I am placing the cursor, and the robot should be able to reach these positions that are numbered by 1, 2, 3, 4, and 5. As you can see, we have been given the values of these coordinates in the z, y, and x plane, so that we can give these values to our robot, and in this way we can calculate the angles required for the robot to reach these positions. Okay, so there are some considerations that we have to consider while designing the robot. For example, as you can see, it's mentioned in the assignment that the orientation is always facing vertically downwards, which means that whenever the robot reaches any particular point, the z axis of the end effector should always be at a vertically downwards position. So we had to design such a robot. Okay, so now I will open my MATLAB, and I will show you the code that I have written to execute this task. Okay, so before I open my MATLAB code and show you the simulation, the first thing is that we will design a robot using some basic robot manipulation and robot theory concepts that we have learned. And once we have designed a prototype of a robot, then we have to test that whether the robot that we have designed is actually able to perform the required tasks or not. Okay, so so these are the specifications of the robot that I have designed for this task. So as I mentioned in the starting, that the solution of the required robot is a 6 degrees of freedom, 6 DOF spherical wrist robot, where there is a total of 6 revolute joints, and the first 3 are responsible for end effector position, while the last 3 joints will determine the orientation of the end effector. So since we know that there are multiple types of industrial robots, a 6 degrees of freedom spherical wrist robot is a robot manipulator in which the first 3 joints are responsible for determining the translation or the position of the end effector, while the last 3 joints are designed in such a way that they only affect the orientation of the end effector. Okay, so I have designed this robot where there is first a revolute joint in a vertical plane position where the axis of rotation is vertically upwards. Then there are two revolute joints whose the axis of rotation of these joints are into the page. Then there is again there is a revolute joint whose axis of rotation is rightwards. Then again there is a joint with axis of rotation inwards, and then in the last one there is another revolute joint whose axis of rotation is rightward, and then there is the end effector. Okay, for the link lengths I have defined a1, a2, a3, a4, a5, a6, and a7. Okay, so initially I have designed this robot, but this robot does not contain the frames, the coordinate frames that are essential while designing any robot for the robot manipulation theories. Okay, so in order to properly assign the frames to the robot joints, there is a very famous and important and useful convention known as the Dennewitt-Hurtenberg convention. So, keeping this consideration in mind, I have in the first diagram you can see as I have written before assigning DH frames. This diagram is showing the joints of the robots without any frame being assigned to them. In the next diagram, you can see I have assigned frames to all the joints and the end effector of this robot. While assigning the frames to the robot, we have to follow the Denevit-Hertenberg parameters. Those are some four parameters that we have to keep in mind while assigning the frames to the joints and the end effector. Okay, so link lengths as okay. So I have mentioned link lengths are defined keeping the desired coordinates given in the assignment. So, for example, if I open back the assignment, in this example you can see when the robot wants to reach position number 2, it has to go in the it has to cover 500 millimeters in the y direction, while there is no distance covered in the z and the x axis direction. Okay, so for example, the coordinates of this point will be 0, 500 and 0, because there will be no x and z coordinate while there is a value of 500 millimeters in the y axis. Okay, so I open back my robot diagram again. So, keeping in view the coordinates given in the assignment, I have assigned the value of link lengths. So, you can see I have given the value of 0.810 meters to A1, A2 is 0.500, A3 is 1, A4 is 0.7. And since I have mentioned earlier that I have designed a 6 degrees spherical wrist robot, so the last three link lengths, that is A5, A6 and A7, will be 0, because in a spherical wrist robot the last three joints are somewhat at a same location, so that they can only affect the orientation of the end effector. For that reason, I have assigned the value of 0 to A5, A6 and A7. Okay. From these parameters, following the Denevit-Hertenberg convention, we then design the DH table for our robot. So, since there are a total number of six joints, the total number of links that our Denevit-Hertenberg table will contain will be six, and for those six lengths, I have given the theta, the alpha, the r, and the d values. Uh, you can follow the Denevit-Hertenberg convention and easily calculate these values of theta, alpha, r, and d. Okay. Now coming to the code that I have written, keeping in mind this robot, I will explain you my code. Okay. In my MATLAB, I have created a script file .m file where I have written the code, and there are some things that we will do in the command window when the code is compiled. So initially, just in the same way as I have shown in the other diagram, I have defined the link lengths. I have initially defined the link lengths in my MATLAB code, and again A5, A6 and A7 are 0, because we are assuming that we are designing a spherical wrist robot. I have also mentioned this in comments. Then I have also, for reference, I have placed here in my MATLAB code the DH table, the DH values. Okay. When we have all the basic data, the link lengths and the DH table, we can then design our robot using the serial link command in MATLAB. To use the serial link command for designing a robot, we first define the links from the DH table. So link 1 is this, link 2, link 3, link 4, link 5 and link 6, using this DH table and the parameters that we have defined at the start of the code. Once we have designed all the six links, we can then join these six links using the command serial link. And I have given my robot a variable name in MATLAB code as sortbot, and the name that it will be showing when the robot is showing on the screen will be garbage recycler, because as part of the assignment, this robot will be sorting the three type of components, three types of parts, namely the plastics, the metals and the glass, from this conveyor, and will pick any particular part from this conveyor and will put it into the relevant container from this conveyor. Okay, so so here I am creating my robot, giving it a name of garbage recycler, and when my robot once my robot is created, I am then defining the homogeneous transformation matrices for desired position. So one thing to note here is that since we were asked in the assignment that whenever the robot reaches the desired position, the axis of robot should must be facing vertically downwards. That is, the z axis of the end effector should be vertically facing downwards. To achieve this thing, I have used an uh, identity matrix having three rows and three columns. And as I have mentioned in this code, the first row will be having 100, then 0 minus 10, and then 00 minus 1. The reason for using this sort of identity matrix for my homogeneous transform matrix is that since the frame 0 is, as you can see in the assignment, the z axis of frame 0 is vertically upwards. So we want to uh, change the direction of end effector in such a way that it should be opposite to the z direction of the base frame. Since base frame is vertically upwards and we want the z direction of the end effector to be vertically downwards, then we can use this matrix 100, 0 minus 10, 00 minus 1 for our end effector. Okay. Next, I am designing five, six different homogeneous transform matrices for my positions. The first position is a position that I have created by the name of default position. Default position where the x coordinate is 0, the y coordinate is minus 0.5, the z coordinate is 0.4. Okay, so here I am defining the homogeneous transform matrix for position 1. Okay, once I have defined my homogeneous transform matrix for position 1, then I can calculate the angles required for the robot to reach this position using the ikine command. To use the ikine command, we write in this way: sortbot, like we have to write the name of robot, then dot ikine, then in brackets we first place the homogeneous transform of the position where we want our robot to go, and then we give the initial joint values. This is not compulsory, you may give or you may not give, but it is a good option so that the reader of the code will know that what are the initial joint values. So in my case, I am giving the initial joint values of 000. Okay, so in this way, the ikine command will give six different values of angle for the robot to reach the position p0. Then coming to the next part is the position 1 of my robot. Position 1 is the position that is defined in the assignment as position 1, where x is 0, y is minus 0.5, and z is again 0. For this position 1, I am again calculating the angles required for the robot to reach this position by using the ikine command, and so on. I am calculating the angle position for all six positions of my robot. Five are the positions, five positions are given in the assignment, and p0 is the position that I have defined as a default position. You can consider it as a home position for the robot. Okay, once I have defined all six positions and calculated their angles by using the ikine command, I can then plot the trajectory that my robot will take when it will go from one position to another position in its workplace, in its workspace. So in MATLAB, we can use two different types of trajectory commands to plot the trajectory of a robot. One is the LSPB trajectory, and the other one is the polynomial trajectory. LSPB trajectory is known as linear segment segmented parabolic blends, and the poly trajectory is a polynomial trajectory. There are some differences in the design and the graph of these trajectories. Once I will run the code, I can show you both these trajectories when I will use this command. So To use the trajectories command, we have to define the time period in which the robot will move from one position to another position in the trajectory. For that, I have defined the time for trajectory with a step size of zero point 0.2 seconds and a total duration of 2 seconds. So t will start from 0, increment in the steps of zero point 0.2 seconds, and then will reach at 2 seconds. Okay, so this is all my code. Now I will compile my code and run a few commands in the command window. So we run the code. So you see, I have created the MATLAB M file by the name of recycler1. Recycler1 is now showing in the command window, and all the variables that I have created, designed in my m.m file, are now executed in the workspace. Okay, so for example, I want my robot to move to the position number uh, position number 3. So that is in the assignment is the position of plastics. So I run the command sortbot dot plot and giving the angle value for position 3, which is Q3. Okay, I press enter. Okay, so now you can see in the diagram, the robot has reached to position number 3 that was shown in the assignment, and you can note that the z axis is facing vertically downwards, as mentioned in the code, that by using this identity matrix of 1 0 0 0 minus 1 0 and 0 0 minus 1, the z axis of the end effector will always remain vertically downwards. Okay, so now I will show you all the positions where the robot can reach. So I have plotted position number Q3. Now I will plot position Q0, that is above position number 1, with some offset in the z value. Note that the z axis will remain perpendicularly downwards. Okay, so you see, now the robot has moved to default position Q0. Let me zoom it a little bit so that you can see the position and the orientation of the end effector. See, Z is pointing vertically downwards and the robot has moved to default position P0. Now we move the robot to some other positions. Q1, Q1. Now Q2 is in the same x and z axis, just there is an offset in the y value. So when I will enter Q2, you will see that the robot will only move in the y direction. Let me zoom it a little bit. So I enter sortbot.plot Q2 and then I press enter. So you see that the robot has only moved in the y direction to a value of 1 meter in the y axis direction. Now I have also okay, so I have plotted Q3, Q0, Q1, Q2. 2 points are remaining, Q4 and Q5. For Q4 and 5, I am going to rotate the plane of my robot so that it is easily visible for us to see. Okay, I place the frame of my robot in this way so that we can see. First, I will again plot Q3 so that we can follow the trend between Q3, Q4, and Q5. So, so this is Q3. Note that Z is pointing vertically downwards. Then we plot Q4. Now Q4 is a little bit further left with respect to Q3 and a little bit upwards in the Z direction. You will see this. See, Z has moved, the end effector has moved both in the X direction and in the Z direction. Now I will plot Q5. You see, now the robot has moved more further in the Z and in the X direction. Okay, so since you can see, now the robot is reaching all the six positions. Now I will use the commands of trajectory to show the trajectory that the robot will take between any 2 points, using the trajectory command that I have defined in my matlab.m script file. Okay, so as mentioned earlier, I have defined two different type of trajectories: the LSPB trajectory and the polynomial trajectory. First, I will plot from the LSPB trajectory, and then I will use the polynomial trajectory function. For the LSPB trajectory, I have defined the variable's name by traj, and for the polynomial trajectories, I have defined the variable names by ptraj, p denoting polynomial. Okay, to draw the trajectory of any robot between 2 points, the syntax that we will follow is sortbot dot plot. In the argument, we will give the name of the trajectory variable that we want to plot. For example, if we want to plot the trajectory of the robot from point 1 to point 2, then we will use traj12. Traj12. So I close this figure so that it will open again, and then I press enter. It's executing. Okay, so I again run this command to verify it once again. Okay, so you see the robot is moving from position 1 to position 2. Now I enter the traj 2 to 3 so that you can more clearly observe the path that the robot is taking from point 2 to point 3. Traj 2 3. See, the robot is moving from point 2 to point 3, and then I use the command traj 3 to 4 for the next trajectory path. Shortbot.plot bracket traj 3 4. Just allow me to change the orientation so that you can clearly see the trajectory path. Now I press enter. So you see the robot is moving from point 3 to point 4. And now again, if I run the traj 1 to 2 command, you will see the trajectory path from point 1 to point 2. First it will move to point 1, and then from point 1 you see the robot move to point 2. Now I will use the polynomial trajectory commands using this ptraj variable. The syntax is same. I will just change the argument in the plot function. Sortbot.plot ptraj ptraj and entering 1 2, and then I press, just zoom it a little bit, orient the workspace of my robot, and then I press enter. So, as it seems in this simulation, the polynomial trajectory seems a little bit more smooth as compared to the LSPB trajectory. I uh, I run again this command so that you can see the difference between the polynomial trajectory and the linear segment trajectory. I run this command again. The robot will first move to point 1 somewhere here, and then will again move to point 2. I press enter. So you see the robot is moving from point 1 to point 2. Okay, now I move it from point 2 to point 3. PT raj to 3. I change the direction so that the trajectory will become more visible. At the moment, the robot is at point 2. Now, after running this command, it will move somewhere here at point number 3. I press enter, then you will see. So you see the robot is moving from point 2 to point 3. Note that in all the cases, the z-axis is always facing vertically downwards, even though the x and y-axis are changing. That's because of this 3 cross 3 rotation matrix that I have used for my z-axis. So, so this was all from my side. Hope you enjoyed the simulation. Thank you.